Start today's class. We have two questions from Samim. One question is how do you verify the two stochastic process is equal? So, to answer this question, we first answer this question: how do you know there are two random variables? X and Y are two random variables. Because stochastic process is a sequence of random variable or is a collection of random variable. So we first know, if I want to know two sequences are equal, we first we have to know how we verify two numbers are equal. So that's why two random variables. How do you know they are equal? They are equal if their probability x equal to y is just 1. It's also called stochastically equal. That means x has takes some values, y if they're discrete, then x has some values x1 x2 xn, y has some values y1 y2 yn. These two set must match, and probability of that means x1 equal to y1, x2 equal to y2, and probability of x1 equal to x is equal to probability of y, x equal to x1 is equal to probability of y equal to x1. That means two random variables are equal. Or we can say in other way, x probability of x minus y is equal to 0 is 1. That means x equal to y, this is almost surely. X equal to y almost surely. You can, in other way, you can say that for every omega belongs to omega, such that x omega x omega is equal to y omega. This probability is 1. All omega belongs to omega. This x omega now y omega equal with probability 1. Now, similarly, if there is sequence, say sequence of random variables, x1, x2, xn dot dot, and y1, y2, yn dot dot. How do you know two sequences are equal? Clear. It is a probability of each term is equal. Xn equal to yn is 1 for all n. And if that sequence two stochastic process, xt t belongs to say t1 and yt belongs to t2. How do you know these two are equal? How do you know two collection are equal? That means your first of all, your t1 must be equal to t2, and xt is equal to yt with probability 1 for all t. So for every t, that say t is capital T is say natural number, set of natural numbers, then x1 equal to y1, x2 equal to y2. If it is set of all integers, then the set of all integers, then x1 equal to y1, x0 equal to y0 with probability 1 with probability 1. So two random variable equal means two random variable equal with probability 1, and x of minus 1 is equal to y of minus 1, something like that. X of minus 5 is equal to y of minus 5. These two are called, then these two sequence or these two collection of random variables is equal. Now question is whether if two sequence, if I have a sequence say 0 1 0 1 0 0 1 and if I say 1 0 1 0 1 0, is this two sequences are equal? No, obviously these two sequences are not equal. But if I say two to set, say, to set. Is that equal? Yes, they are equal. As I said, they are equal. But as a sequence, these two are not equal. These two are not equal. So that means there's a ordering in the set. Ordering in the set. So if I say there is a collection, say x1, x2, x3, so only three elements. And another collection is y1, y2, y3. The question is whether these two are equal. How do you check these two are equal? Is this like that? X1 equal to y1 with probability 1, x2 equal to y2 with probability 1, x3 y2 y3 probability 1, or it may be x1 with y1 with probability 1, and x2 is y3 with probability 1, and x3 is y3 is y1 is with probability 1 is equal to x3 is equal to y1 with probability 1. Should I say these two stochastic processes are equal? That's the question. The question is this: if I have a such a relation, x1 is equal to y3 with probability 1, and x2 is equal to y1 with probability 1, and x3 is equal to y2 with probability 1, is this two stochastic process equal? The answer is no. So that must be some ordering in this index set. So in indexes, if it is sequence, is that order is sequence, but it's not a sequence; it's a collection. Or if it is a finite, we have a n tuple x1, x2, xn, y1, y2. You have to match x1 with y1, x2 with y2. But if they're not ordering, the two set index sets, say, then how to match which match with which one? That's the question. Which match with which one? So if something starts, say x1 equal to a random variable which takes probability 0 or 1 with probability half, then x2 is a random variable with take probability, say, -1 and 1 with half, 2, say, half. So that means the particle at the time 1, it is either maybe 0 or maybe 1 with half of probability. In step 2, it is -1 or say 2 with half. In step 3, it is -3 and 4 with half, something like that. And another random variable is such a way that in step 1, this probability with -5 and 6 with probability half. Step 2, it is 0 and 1 with half. Step 3, it is step -3 and 2 is half. No, these two random variable stochastic cannot be equal because the conditional probability will be different. The conditional probability will be different. So there is a conditional probability thing. So that must be. That's why we take a time parameter, index set as a time parameter. If it is a sequence of random variable, it's already ordered. If you take a collection of random variables, which is not a sequence, then that collection must be an ordered set. Is it like a real number? It sometimes is a subset of real number. So that the collection is xt, t belongs to t, and t is a subset of real number. Subset of real number. Now, in a collection that may not be an ordered set. Any collection. So we have a collection of set, say A alpha. Now this alpha in the index set, that may not be odd. That may be any abstract set. Maybe something like we take A1, A2, A3, say A4, A1, A2, A4. But we can take such a set, collection of sets, such as B cow, then B cat, then B dog. You can take such a set, collection of sets, and B cow, the index of cow is a set. This is a set of say A, B, C, and B cow, B cat, and B dog is another set. Say B cat is a D, E, F, say B dog is some say A, E, H, something like that. Is this okay, Tamim?
Yes, sir.
So just to recall of the previous classes, in the previous classes what we done, first we define what is random walk. We define random walk in a one-dimensional case, one-dimensional case, starting with some zero initial distribution, and from random walk we check some conditions that in random walk that conditional probability xn plus x given xn equal to I, and the previous thing, this does not depends on the previous, this the probability of some future event is depends on only past. Once I say this is a future, past, present, that means there is a ordering in the index. That means there is ordering of index in the index set. Then we find the distribution, joint distribution, marginal distribution, and from this we this is a property of the random walk, and this is not only the property of random walk. There are several sequence of random variable stochastic process which have this property. This is called Markov chain. So random walk is a Markov chain, and the Markov chain is actually characterized by this probability, and this is something called x comma y from y to x. Characterized by this. If I know all this p y x for all x and all y belongs to a state space, this is called state space, where this actually this is union of the range of xn, and if it's a continuous, there is support. That sequence is discrete x1 x2 xn, but that the output of the x1 x2 xn may be continuous. There are continuous, discrete, continuous, four cases. The index set is discrete, but the random variables are continuous. But we now concentrate our talk in only discrete sequence of random variables, and the random variables have only discrete or finite, discrete or finite, not continuous. So this is called transition probability, and if it is a finite state space, that means there is such a transition probabilities are finite. If there are n many elements of state space, there are n squared, so there is a matrix. If I state s equal to 1 to 3 up to n, that means a p11, that is not probability, is a p is a function p xy p11, but probability of x equal to xn plus 1 equal to x given xn equal to y. So, and we define some another function px for a fixed x as this from x to y, and we saw this is a PMF. This px is a PMF. we assume that this all the random variables are discrete, and we find this. We find how to find transition function, matrix from the transition function, the conditional property, and from the conditional property, how do you find the all the transition matrix, and from transition matrix to all the conditional property. From the conditional property, how do you find we, we, we learn how do you find this joint distribution from conditional, and we know another distribution we call initial distribution. If we have initial and conditional distribution, we go to the joint, and from joint we go to the marginal. So from conditional initial we go to the joint, then joint to marginal. This is the way: conditional to joint, joint to marginal. And we discuss a special case where Markov chain with two-state Markov chain, and we find all these joint, marginal distribution, and then the limiting distribution. Limiting distribution. Limiting distribution. And then we discuss the Markov chain with d plus one state, and there is a d plus one plus d plus one transition matrix. And we see some result on marginal, which is actually this, which is actually initial distribution with p into p to the power n, where p is the transition matrix. Now next we define m step transition function. Transition function, which is actually p to the power n. And how do we define this? P to the power m. That means from x to y, we shift from x to y with m step, not one step, m step. And that is actually sum over all this intermediate step, x to y1, then y1 to y2, say y1 to next step y1 to y2, then ym minus 2 to ym minus 1, and then the last step ym minus 1 to x. And we should take the sum over all y1, y2, ym minus 1. They are m minus 1 sum. If they are one step transition function, that means transition function, there is no summation. If they are two step, there is only one summation. If they are m step, that means in a graph, if we have in x, we want to go in y, in some say 3 step, we can go for in first step somewhere. From there, we can go in the second step somewhere here, maybe here to here, second step, maybe then here to here in the second step, something like that. From here in third step, we can go here, we may go here, we may go another somewhere. From here, maybe we in second step here, or maybe somewhere here, and then the final step we and also from here to here directly, and here. So actually it's a graph, and in graph, you know what is graph? Graph, there are some vertices. Vertices are the state space, and there is a connection. Connection means there is a transition, positive transition probability, that will be edge. Edge means there is a positive transition probability, and to go somewhere to somewhere, we need a path from x to y of length m length path. We have to take all m length path, and then you have to take the product of every transition function probability, and then take the sum all such path and take the probability of each path. Probability of each path is a product of every step, and this add over all this path of length m which start from x and go to the y. So this is the graph theory is very important in the Markov chain. That's why the knowledge of graph theory is very important on the transition in the Markov chain. So sometimes some properties of Markov chain we next in later part we will see that the properties of Markov chain, that transition state, transient state, recurrent state, will describe with some graphs. So graph means not a graph of function, it is a graph invented by the Euler graph theory. Now today start with one-dimensional random walk in general case. What is this? Take some random variables xi1, xi2, it's a sequence of random variables, integer value. That means the state space is integer valued random variable, IID, valued random variable. And this is IID, so it is a common density having common density. Sometimes PMF also called density. Density means if it is discrete, then it is a PMF density. If I say density F and if xi1, xi2 are discrete, then it is not a PDF, it is a PMF. So PMF and PDF we use the common term density. Now say x0 is an integer value random variable. Be an starting random walk start from x0, be an integer valued random variable, and this is independent of xi i's. So that means xi1, xi2, xi are each one is independent, as well as this x0 independent with xi1, independent with xi2. And now define x1 is x0 plus xi1. Then x2 is x1 plus xi2, which is actually x0 plus xi1 plus xi2. Then xn defined like x0 plus xi1 plus xi2 plus xi1. So in special case of random walk, we actually use xi1 every xi I as g1 or -1. In previous example of random walk, we take xi I is equal to 1 or -1. So you can add 1 or you can add -1. That means one step forward or one step backward with probability say p and with probability 1 minus p. And it is half of, then it is a previous case. It's the first class what you see in the random walk. Now this is not a xi1 is now may not be 1 and -1. Xi1 maybe with probability 1/3 it may be 0, with probability 1/3 is 1, with probability 1/3 it is minus. That means it start from 0, it go to the 1 with probability 1/3, with probability 1/3 can go -1 and with probability 1/3 stay there. Maybe xi1 is a random variable which takes 5 values, say -2, -1, 0, 1, 2. That means with probability say 1/5, 1/5, 1/5, 1/5. That means for every step that can go stay there or go one step forward or two step forward or one step backward or two unit backward with probability equal probability 1/5. Now this is a generalization of the random walk, general case. Now this we can show that this is a Markov chain. We can show that easy to see that this is n greater than or equal to 0 is a Markov chain. We can easily show this is a Markov chain. And what is the transition function? Easily you can check the transition function. You start from x and you want to go y in the next step. That means your xn plus 1 equal to y, given that your xn is x. That means what? That means xn plus 1, what is it? It is xn plus xi n plus 1, which is y, given that xn equal to x. What is the probability? This is nothing but what? This is probability of xi n plus 1 equal to y minus x, given xn equal to x. So this must be equal to this. You can easily check that. You can check this is a homework. You can check this. All these exclamation marks means homework. You can check these two are equal. And since xi n plus 1 and xn is independent, that means the probability of xi n plus 1 equal to y. But this is a with the same density of f, so it is f of y minus x. In a special case, this f of 1 is half and f of minus 1 is half. So you have to find there is a Markov chain. So to how to find the Markov chain? You also check that you have to check that this xn plus 1 equal to y given xn equal to x and this other xn minus 1 equal to some xn minus 1 xn x0 equal to x0 is nothing but probability of this xn plus 1 to y given xn equal to x. And this you can use using this independency. So you have to check this also homework. There's two homework. You have to check this one. You have to check this equality. Now then, what will be the joint distribution? X0 equal to x0, x1 is equal to x1, xn equal to xn. The joint distribution will be, it will start from x0, so it is pi of x0, pi 0 x0, pi 0 is the initial distribution. Then you go x0 to x1, that means x1 equal to x1, that is x1 minus x0. Then for this mass function or whatever, this x2 minus x1 density f of x n minus x n minus 1. Or you can write this as like that, x0 transition function from x0 to x1. Then that can start from x0, x0 to x1, x1 to x2, or xn minus 1 to xn. And again, you have to check all these things. You have to check this portion. Again, homework. Again, there's a homework. You have to check this, and then you can check easily by the previous thing. In previous class, we see how we find the joint distribution from the conditional and this initial distribution. Now there is a special case. F of 1 equal to say P with probability 1 step forward, with probability -1 1 step backward, and with probability 0 remain there. Obviously P, Q, R are all positive, and P plus Q plus R may be 0, then it is just a random walk in the special case, very fast cases, random walk. And if R is not positive, then it is not only this special type of random walk, it is not a that first kind of random walk, it is a special type of random walk. It can stay there for the next move, in the next move. Is also called birth and death chain. Why is the birth and death chain? That means somewhere, some in population, some say n numbers of elements are there. In next 1 hour, it may be remain n, maybe n plus 1 or maybe n minus 1, one death. Maybe one death occur. If death occur with probability q, it birth occur with probability p, only one birth and only one death, and maybe no birth, no death with probability r. You can, in a graph, you can do this from I to, you can go I plus 1 or I minus 1, I plus 1 or maybe in I minus 1. You can from I to go that with probability p, from here to here equal probability p. You can go back with probability q, you can go back with probability q, from again forward with probability p, here with probability p, and you can stay there with probability r, stay there with probability r, stay there with probability r. This is a graph of this Markov chain. And again, you can find on this transition function, this is homework, find all these transition functions. These transition functions you can easily find. Function, then this margin conditional is there. This is at the conditional. This given qualities are conditional, then joint, and then marginal. But this will be not easy. Finding joint and marginal will be not easy, because how do, in a finite case there is a concept of transition matrix, but here how to relate this idea with a matrix? Then we have to get a new idea called infinite matrix. What is infinite matrix? This is a sort of infinite matrix. There is infinite matrix. No in somewhere. Say 1 by 1, 1 by 2, 1 by 3, 1 by 4, dot, 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 dot. So then 2 by 1, 2 by 2, 2 by 3, 2 by 4, something like that. So we know the matrix is actually, this infinite matrix is nothing but a function from n cross n to some real number, or in this case, it's state space. So it's like a matrix, n cross n, infinite matrix, because the first element will be f of 1 1. If 1 1 is the first element, if 1 2 is the second element, dot 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 dot. If 2 1 is the first element, and dot dot dot. Infinite sort of thing. So we can think about this infinite transition matrix. So how do you think this? Okay, script space is a countable. It is infinite but countable. If it is a uncountable, there is a problem. It's countable, infinite set. The infinite set, but is a countable, not uncountable. If it's uncountable, there is no question of matrix. So we can take, without loss of generality, we can take this script S as a Z, or maybe natural number, or maybe natural number union 0. That means from 0 to 0 1 dot, maybe 1 to 2 dot, or maybe 0 1 minus 1 2 minus 2 everything. Now it is a Z. If it is Z, then what will be the infinite transition matrix? This will be some element of Pij, where Ij, where Pij are the probability of xn plus 1 is equal to j, start from j to I to j, sorry, it is xn, and actually which is same as, this does not depends on, this probability does not depends on n, so it is same as x0 to I, which is this for all ij belongs to j, or maybe n, or maybe n union set containing j. And how do you define this infinite matrix, addition of two infinite matrix? Is it element wise? P plus q is p, the element of p plus q, ijth element of p plus q is a pij plus qij. And what will be the product then? We know how to get the product of finite case. Take the ith row and the jth column, and we take the dot product. Similarly, for the infinite matrix, the same thing. P I t and p tj, and take the sum over all t. T is now is an infinite set. Maybe z, maybe it is 0 to infinity, or maybe whatever the set. If it is z, it is minus infinity to infinity. Now again, there is a question. This is a the probability from goes from, there is a p I j. In two step. It is actually in two step. From I to t, t to j. Two step transition function. But there is a question of summation. So there is a question, there is convergent of that. And if there is a countable set like z, what term we will take first? Whether it is take first the 0, then 1, then minus 1, then 2, then minus 2, or we will take first 0, then 1, then 2, then minus 1, then minus 2. That's the problem. How do we add this? All this sum, all this at, something like at t belongs to z. How do we add? That's the question. How do we add this? Is not just a0 plus a1 plus a2. It is not that. How do you add this? Whether it is this, whether we add something like then minus 1, then 2, then minus 2, or maybe a0 plus a1 plus a2, take 2 term forward, then 2 backward. Is this all this sum are equal, or this partial sums are equal in both cases? May not be. If it is an alternative sequence, or maybe negative term, may not be. But if it is a positive term, there is a very important result in real analysis. If the sequence, the series has all the term are positive, then you can rearrange. If it is a convergent, if you rearrange, or you take the bracketing, then that after taking bracket or rearrange the term, this sequence, that modified sequence have the same limit. It's convergent to the same limit. But if it is alternative, then it is a if it is some negative terms is there, it is not true. But here all are probability. Since they are all probability, that means this converge, and you can take any one first. You can take 0, then 1, then minus 1, then minus 2, minus 2, or maybe you can take 0, 1, 2, 1, minus 1, minus 2, 3, 4, minus 3, minus 4. Any way, any ordering, but the sum is equal because they're all in positive terms. But why they converge? That is easy, because every term actually PIT, PTJ, this is every term is actually less than or equal to PIT, and if you take the sum, then sum is just, it is 1. So it is bounded. This sequence, this series is bounded every partial term sum is bounded and is a positive term, so it is increasing partial sum of the increasing sequence with bounded increasing sequence, and we know the bounded increasing sequence converge to its least upper bound. That is the converge, and this series converge. The series has a value. And this is defined like P2ij, two-step transition function. Similarly, you can do with n step, and you can easily show that this again bounded and bounded by 1, and then this is a positive term, so it should converge. And remember this infinite whatever this infinite or finite matrix is a P matrix, infinite finite. This row sum will be always 1. Row sum from 1 0 to 0 0 to 1, this sum is 1, but this column sum may not be 1. This may not be 1. That may be less than 1, maybe greater than 1, because the column sum is from 0 to 0, from 1 to 0, from 2 to 0, from dot 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 n to 0. That may not be 1. That may be n. Maybe everything leading to 1, from 0 to 1 is probability 1, from 1 to 1 is probability 1, from 2 to 1 is probability 1. That means after 2 step, next step, the second is everything is 1. So the probability of x1 equal to 1 is 1. Then the column sum is n. And there's another important chain. It's called unphased chain. It's the last topic for today. Next class we start stationary distribution, unphased chain. This is modeled by the gas exchange formula. This is modeled by gas exchange formula. Model for this is first model for exchange of. Basically, this stochastic process came from the physics. Basically, it start from the Brownian motion, exchange of heat or heat or gas molecule of two isolated body, between two isolated body, two isolated body, isolated bodies. It's basically stochastic process came from this physics, Brownian motion or this kinetic theory of gases, this gas. This molecule or heat energy conversion, this actually the stochastic process came from that, because in physics or physicists of the inquiry, now it is there is state, after 1 minute or 1 hour what will be the state. So again after 1 hour what will be, what may be the state. So that means everything is random. So we don't know whether after 1 hour what will be the stage, and after 2 hours what will be the stage. But we know if after 1 hour that will be the stage, then after 2 hours the probability of that will be the stage will be that and that and so on and so forth. So something like Markov chain. If after 2 hours there is a cloud in, then after 3 hours there may be rain. But from now the probability of rain after 3 hours maybe say half. But if after 2 hours there is a cloud, then the probability of rain in the third hour is 0.9, something like that. So the weather forecasting is also a Markov chain. So mainly in physics. And this, what is the gas molecule particle criteria? Actually there is a 2 box, one is 1 and one is 2, and the box there are some level ball, say the ball are 1 2 level by 1 2 up to D, the D level, and some balls are in box, some are in box 1, some are in box 2. We don't know how many are there. So initially some box in box say 3 balls, here say 5 balls, something like that. Now I choose one integer. I choose one integer randomly from 1 to D. I choose one integer from randomly. We know this is the randomness sign, dollar sign. We choose an integer randomly. Randomly means uniformly distributed. So every ball can be chosen with probability 1 by d. And if it is, say, we choose 3, if it is a box 1, we just replaced in the box 2. We remove from the box 1. So an integer is randomly chosen. So there are 2 boxes, 1 and 2, and d balls labeled 1, 2 up to d. And initially, some of balls are in box 1 and rest are in box 2. Now an integer is selected. From 1 to up to d randomly, uniformly. And that corresponding ball remove from the box, from its box, and placed in the opposite box. That is the basic idea of heat exchange, or any type of particle exchange. So if there are 2 boxes, two room or 2 chambers, and one chamber has say more gas molecule, high density, and other box or other room is a low density. So they're in a box there are 100 gas molecule, and rest other one is has 20 only. Now, so ball, that means here is particles are moving. Actually, you know that in Brownian motion, all the particles are randomly moved in the 3-dimensional. It's actually 3-dimensional random walk. Now, can one ball go to the another box? Yes. It's not only true that always from the high density particle room, the always ball coming from that and go to the lower density. That's not true. Maybe from lower density, maybe go to the higher density, but the probability is low. Obviously, the probability is low because this randomly moving, but the probability is low because there are less number of balls. So with probability 1 by 6, they're from lower to higher density, and from 5 by 6, they're from higher to lower density ball room. Ball maybe go from lower to higher. Now, every time they say, if I assume there is a very small amount of time, unit time, only one ball is exchanging. That is just modeled by this ball exchange in the 2 box situation. Now, this is an opposite box, and xn denote the x0 is the initial case, xn is the number of ball in say box 1. So x0 is the number of ball in the box 1 in the initial starting. So that then the question, after n times, n unit of times, how many balls will be after say at every second there is only one ball changing. After 10 seconds, how many balls will be in box 1 or box 2? It is not true that 20, 100 will be 30 and 90 after 10 minutes, 10 seconds. It may be 28 and 20 and what? Say 110, 120, so 28 or maybe 92. And so with some probability, everything with some probability. There are 11 there are 21 cases maybe all the 10 balls from the low density go to the high density. Very low probability, but maybe so happen there are 10 and 90 after 10 minutes, 10 seconds, 10 unit time. So extend the number of balls in box 1 after in step, after the nth dial. Now, what is the state space? Obviously, the state space will be 0, 1 up to d. It can't be less than 0. Number of balls must be greater than or equal to 0, maybe 0, or cannot be greater than or equal to d because only d balls are there. And what is the transition function then? Transition function, you can easily check that transition function is, it may be, sorry, the transition function, the p from x to y. Now what? Y can be x minus 1, yes. Y can be x plus 1, yes. And y can be x, yes. Y can be any other thing, yes, but with probability 0. So elsewhere it is 0. Elsewhere it is 0. So one ball must change. And what is the probability that next step it will be x minus 1? That means one ball from the first box go to the second box. That means the first box has x many balls. After one step it will be x minus 1. But what is the probability that one ball from box 1 go to the box 2? That means you are choosing that random integer from 1 to d. That will be from the box 1. But how many balls are there? There are x many balls. So you are choosing one integer randomly from d integers. And what is the probability that that will be in the set containing the x integer? That will be x by d. And it's just 1 minus x by d. So it is a random walk actually with this p equal to x by d. And you can easily check what will be the transition matrix. The transition matrix is, if it's from 0, 1, d, 0, 1, d, your transition matrix will be clearly from 0 to 0 is 0. So only these elements will be there, these elements, no other elements will be there. It is 1, 0 to 1 must be 1, 1 to 0 it is 1 by d, 1 to 1 it is 0, it is d minus 1 by d, and this rest are zeros, this rest are zeros. Only two positive number in each row. In the first row there are only 1, and the last row there is also only 1. This is 1, this is 0, because from d to d minus 1 this is 1. And here this matrix is just shifting. 1, 2, 3, there is 2 minus d to 0, then d minus 2. This is shifting, this matrix is shifting for right side. So this is a transition matrix. For the unfazed chain, this is called unfazed chain. And stop here. Next class we start with stationary distribution, very important and interesting topic, stationary distribution. So this for today's lecture.